Hi, good morning. The computer has some issue today, so I restarted. It takes time. Do you have any more question you want to ask before we start? Any questions? Okay, if there's no question, we're going to continue where we started on section 12. 1.12, the title is force of interest. So essentially, the calculation of it is based on the fact we are trying to find the limit of the limit of the interest function. So essentially, it's you can consider force of interest as the instantaneous rate of change. So before, whenever you want to calculate an interest, you will have to identify a time frame. So the interest is calculated by the ending value minus the initial value divided by the beginning value. That's how you calculate interest if you have a time interval that has a length of 1. Now, if the time interval gets shorter, of course, your interest will be calculated by this kind of formula, and that is for a shorter time frame. But the idea is, what if you magnify that shorter time frame interest to the whole year? Then the interest rate becomes project onto the whole year. That's this. So when m goes to infinity, that means as your time interval gets shorter and shorter, this limit value is derivative of the accumulated function divided by the accumulation function. So we define this a prime t over at as the force of the interest function. Okay, so the force of interest is it's in fact, it's an instantaneous rate of interest. So it's similar to the R, the D. So all the other interest notion that we had before, but this one definitely is taking a limit format. So this is our first definition of force of interest. And last time in class, we talked about if you have a simple interest, then your force of interest is interest rate divided by 1 plus RT for your simple interest formula. And we also talked about if you have a simple discount, then the force of interest is d divided by 1 minus dt. So again, that's a rational function. And the third example is if you have a compound interest, then your force of interest is natural log of 1 plus I. And that I is your annual effective interest rates. And these two are equivalent. So interest rate of I is equivalent to a force of interest, instantaneous interest of ln of 1 plus I. And then this is the only constant force of interest. All the other one, the force of interest will change based on the time interval t. All right, and now we come up with the idea that the a prime t divided by at reminded us a derivative of natural log function. Derivative of a natural log of other function, you have to have this function in the denominator, and numerator has to be derivative of the inside function because the chain rule. So force of interest have another definition, that's a derivative of the natural log of the accumulation function. So that's sometimes poses a convenience when you have exponential function in your accumulation function and taking natural log of your at, then separate all these terms, which makes the differentiation a little bit easier. And that's this example. All right, and then we move forward that because of force interest function and accumulation function had that relation that made it possible for us to calculate force of interest if you already have AT, or calculate AT if you already have the force of interest. So in reverse, force of interest is a derivative of the logarithm of AT. Therefore, if you want to calculate AT, you will integrate the force of interest and then take exponential functions. We have to reverse the effect of the differentiation process, the effect of the logarithm process. So the inverse of differentiation is integration. The reverse of natural log is basic exponential function that causes us being able to calculate AT. So if you think of the relation, this relation there, that made it possible for us to devise a plan for calculating AT. So that consequently AT equal to e to the 0 to t integration of delta r dr. And then here we have to change the notation because t being the upper limit of the integration, so the integration variable cannot be t anymore. So the bottom formula is our formula for calculating AT if we already know the delta t. Any question? Okay, so we have example on how we do this. All right, this is one of the questions. Suppose we have the force of interest formula. We're going to find the corresponding accumulation function. All right, so the plan would be remember the formula. If you already have the force of interest formula, this is how you calculate AT. So by reading the question, you realize, hey, I have the force of interest. How do I calculate AT? What would be that connection? What would be that formula for the change between the two? So that will be the formula. Right, just all we have to do is plug in delta R. Originally it was delta T, now we have delta R being the confliction variable. T has to be the variable for AT, so then the integration we have to use a different variable. In this case, we're using R. So now the rest is really plug in the calculation for the computation. To save time, I wrote everything down in the way I think it makes more sense. These calculations already have a solution in the book. What I was writing is providing more detail to the process. The book do have a very formal presentation of the solution, but I'm writing it in a really informal way. So based on this formula AT, you realize we have to finish calculating the integration in order to finally write the AT. So delta T dr, delta R dr integrated is the focus of the question. Instead of 3 over 1 minus 3t, I write 3 over 1 minus 3r for the integration. All right, so there we have the integration, a little bit particular. So the one I blocked is just to explain the integration. So to me, because the integration variable is r, but then the integration limit is t, that made it a little bit complex, has multiple variables in the same sense. So I decided maybe we should calculate the indefinite integral, finishing that, and then finally plug in the t. So down here in the orange block, I'm just calculating the indefinite integral just to get a formula. So forget about the t or 0, we just finish kind of integrate this. In calculus, when we try to do this kind of integration, what we do is simplify the notation. What's causing the complication is 1 minus 3r. So instead of calling 1 minus 3r as a u equal to 1 minus 3r, and therefore du equal to negative 3 dr, and therefore dr equal to 1 over negative 3 du. So that's the change the dr. So dr being conformed or converted to 1 over negative 3 du. That's called the change variable. And then I already identified the denominator as a u variable. And that really changes how the integration is done. So this process is substitution method for the integration. Then the 3 can be canceled, negative 1 can be burned out up to the top or to the outside of the integration. It's integration 1 over u, and we should know that according to the integration formula, 1 over u integrated is logarithm natural log of u. We still have the negative 1 as a coefficient. So there's a negative natural log of u plus c. And since it's a change variable, we know that u equal to 1 minus 3r. So there's everything in the orange block is explaining the indefinite integral. Any question? So if we already have that, all we have to do is take this one, and I'm going to plug in 0 for r and plug in t for r because it's a definite integral out there. If you plug in 0, it's natural log of 1, which is 0. So all we have to do is focus on the upper limit. Plug in t for r, you have negative natural log 1 minus 3t. The negative outside the logarithm is actually negative 1 power inside the logarithm. That's actually 1 over 1 minus 3t. So I realize that will be what's happening. So why are we writing it to a total logarithm? Why do we combine the negative into the logarithm? Because in the end, we're doing e to something. So I'm hoping that e will cancel the natural log. But e can only cancel the natural log if they are together. So that negative outside the natural log will be in the way. So I bring that negative up to the top. So there we have it. So e to the natural log of this whole thing. Cancel the e with natural log, and that's our accumulation function. So that's the solution to the question. For a smaller t, you can remove the absolute value. So at is actually 1 over 1 minus 3t. So the absolute value sign is not absolutely necessary unless we went over the size when the t is too big. But then again, this force of interest function should only work for shorter time frame. So t should be like less than 1/3. And that way we don't have to worry about the absolute values then. Any question? All right, so this is one example where accumulation function is being calculated from the force of interest function. And then this is the end of 1.12. 1.3 is super short, so I decided not to make a single file for this. 1.13, the whole chapter is organized in the way some sections assume you know calculus, some sections do not assume you have calculus. So 1.13 is for those people who do not have calculus. So instead of studying 1.12, you study 1.13. So this is a very short section. Okay, so this example saying that this is just one single example in that section. And all we have to remember is that the conversion between the compound interest and the annual effective interest is delta equal to natural log of 1 plus I. Here we have a question saying that, so suppose you have a compound a continuous interest of 3.5%. A person deposits 3,000 in the bank, and what will be his balance 4 years later? So it's a typical question of calculating future value if you already have present value, right? Continuous compounding. So the question will be, if you want to calculate future value, you take present value, multiply the growth function or the accumulation function, that's your future value. In the continuous increase, what's the accumulation function? Is e to the delta t, right? In this case, all we have to do is plug in the e to the delta t. So here is the calculation. It's a really short calculation. 3,000 multiply e to the delta t. This is says 4 years later, so your time is 4, and now that's all the calculation. So that's all 1.13 is really short. Any question? So I assigned a homework assignment on 1.12, but I didn't assign anything for 1.13 since I think that's kind of incorporated into 1.12. And for some students, they will pick and choose a section. If we choose 13, we probably gonna skip 12 and so on. So for some finance students, they don't even care about 12 because they don't want to study the relation. They just want to remember the formula. The assignment, I think I assigned on section 12 is over the force of interest assignment. And we can try to practice something related to 12 force of interest. So force of interest assignment are mostly like this. You were given the force of interest formula. The question is calculate cumulative value. Obviously, you have to know your accumulation function, and you integrate the force of interest and raise it to the power e to get your accumulation function, and that allows you to calculate future value. Next problem. And most of these questions are in a scenario where the force of interest is given. You're trying to determine the accumulation function. All right. So we're going to try one. And here I have a bigger question I'm hoping to practice with us. So here, bill as account and the interest at a constant accumulation function of annual effective interest rate of K over 12. So we seem to know annual effective interest rate, which we actually don't. There's an unknown constant K in there. Joe's account earns the interest at a force of interest of delta T, that's 1 over K plus 0.25 T. At the end of 4 years, the amount in each account is X. Calculate the X. Effective interest rate. So to solve this question, we kind of have to know what's the relation between the annual effective interest rate and the force of the interest function. Okay, so we're gonna try to look, I have to admit, I didn't really work this out before I assign it. The accumulation function AT, okay. The annual effective interest rate is the value 1 year is A1, A0 is 1. Okay, so your annual effective interest rate I should equal to A1 minus A0, or you can see it's A1 minus 1. And we also know that the force of interest, the AT equal to E to the integration of 0 to T, and we have to integrate our force of interest, 1 over K plus 0.25 R dr. So that's going to be that should be our accumulation function. So we would do similar things that as we did in the example I showed earlier. We have to integrate the force of interest function in order to identify the accumulation function. There's a small problem being carrying the K in the process. So we have to solve for the K in order to do the calculation. We see amount in each account is X. So that must be the A4. We're supposed to calculate A4, but to know A4, we first have to know AT. So let's try to use all these relations, probably calculate the K in the process. The annual effective interest rate is K over 12. So I'm guessing the 4-year value should be 1 plus K over 12 to the power 4. It's a 4-year interest. Constant annual effective interest rate, or compound interest. All right, so let's see how it's being calculated. I was trying to delay the integration process. So 0 to T 1 over K plus 0.25 R dr, which should be calculated first. So this integration, if we do the indefinite integral, it will be this, and then the integration. What I did earlier was using U substitution. I don't know if it's too lengthy to do it this way. So then du is going to be 0.25 dr. And that also means dr equal to 4 times du. So that changes the integration to, this is equal to integration of 1 over u after the substitution. Dr will be 4 times du. The integration will be natural log of 4 times natural log of absolute value of u, where u equal to K plus 0.25 R. So that's the antiderivative. Using that into this, so then the definite integral is going to be 4 times natural log of K plus 0.25 R, plug in 0 and T. Okay. This is natural log of it's a 4. What is the power 4? K plus 0.25 r to the power 4 at 0 and t. The value of this function at t is natural log of k plus 0.25 t to the power 4 minus natural log of k plus, well, k plus 0 to the power 4. So that's the right, that's the integration value. This is a natural log, so it's a natural log of k plus 0.25 t over k to the power 4, because subtraction in the natural log is division inside the natural log. That will be helpful. Is it okay? All right, so that will follow through when you try to calculate the accumulation function. It's e to the natural log of what we have there. Natural log of this is k over k, so that's actually 1 plus 0.25 t over k. This is all to the power 4, so that's our accumulation function. And then the natural log will cancel the e, so I have at is equal to 1 plus 0.25 t over k to the power 4. Any question? All right, so you have to solve for the k. So A1 is going to be 1 plus 0.25 t, t equal to 1 now, 0.25 over k and raised to the power. That's A1. And what will be the interest? So this has to minus 1. That's the annual effective interest rate, which is like A1 minus 1. That's our I. Now this says that the annual effective interest is actually k over 0.25. So that will lead us to the right number for k, but it didn't. Over 25. Unless so we could solve the k from here. So what we're going to calculate is A4. What's A4? A4 is going to be 1 plus 0.25 k to the power of. So, right, accumulation function is this. To calculate A4, we're going to make a t equal to 4. So that's 1 over k to the power 4. That's when t takes on the value of 4. So that's A4 that we were supposed to calculate, right? So it would be better if we know the k value. That would be a problem not knowing the k. So I thought this equation would actually solve the k. I thought everything would work out, but a difficult equation to solve. All right, let me come back to this. I feel like I know everything, but I don't with that last little thing. Instead of spend more time, maybe we all think about how to finish this. The actual value at 4 will have to be calculated once we finish. There always a k. The annual effective interest rate k is not given. From here, there may be a couple of directions. You can see the interest rate, annual effective interest rate is supposed to be a really small number. So you can try a small value like k equal to 1, see if it's making the left side equal to the right side. Solving equation is all about finding the value that causes the left side equal to the right side. So it's possible to try a small number k to see which one works out. That is what we call in calculus intermediate value solution, right? You make k equal to 1, calculate left, calculate right to see if they're equal. If the one side is smaller or larger than the other side, you adjust the k in that direction. So you maybe gradually to calculate the answer to the equation by intermediate value, like adjust the k value, bigger or small. And we know k has to start from a smaller value. So I would recommend starting with 1 or 2 on the k value and maybe adjust to k 0.5 and so on. That way we can slowly find out the true value of k. Once we have the k, we'll be able to calculate A4 based on our formula for AT. We're supposed to calculate A4, the value at 4. This question is a little bit weird. I pulled this out of the question bank without trying it myself. I'll get back to you if you're not already know the answer by next class. But this kind of poses the situation that I might as well find a better example for this. Okay, so let's look at the first question on the homework assignment so we can have some practice over what we intend to do. All right, the process is similar to what I was doing on the board, and you have the force of interest function, the delta t is given. So T represent the time since January 1st, 2004. We're saving Stan invested $1,000 in this account, earning that kind of force of interest. Questions calculate the cumulative value of the fund. I think it should be called like the amount, the balance of the fund by January 1st, 2016. All right, so that's kind of like after the initial time, the 2 year of interest, right? So you will take the 1,000. This is a more typical scenario with no unknown coefficient in the whole setting. So let's try to pull that and at least work out one example that we can do. All right, so here we have. First, we will calculate AT, and based on our formula, AT is equal to e to the natural log of e to the integration of 0 to t delta t, and we have a delta t that's 0.1. And to change the variable, let's use r minus 1 to the power 4 dr. That's our AT. We're gonna try to find the AT. The actual calculation for the cumulative value of the 1,000 should be like 1,000 times A2 accumulated for 2 years. 2004 January and 2006 January, 2 years has passed. So if you want to calculate the final answer, you have to know AT to begin with. So AT is equal to e to the integration of. It's a power function. The antiderivative of power function is also a power function. So the antiderivative is 0.1. Power 4 after integration should be power 5 over 5. And we put in the integration of 0 and t in here. So this is e to the 0.1 over 5. If we put in t, it's t minus 1 to the power 5. If we make 0, so it's minus 0.1 over 5 to the power of 1. Actually, it's plus if we plug in, right? It's negative. 0 minus 1 is negative, so it's negative 1 times. In fact, are we okay? So that's what we have, and that's our AT. So once we know AT, there's no natural log, so there's really no cancellation of the e. So I have to kind of calculate exponent of a to the power 2. So it's e to the power of 0.1 over 5, and then we have 2 minus 1. That's 1. Okay, and then 1 to the power 5 is that. So 0.1 over 5 over 0.1 over 5. So the accumulation function for 2 years is e to the 0.2 over 5, you can plug in this into the calculator to know the value. So this A2 value has multiplied 1,000. So the final answer will be 1,000 times e to the power of 0.2 over 5. Okay, there's the explanation. So that's so a little over 1,000, 1,040. That's the value at time 2. Most of these questions are following that tone, and what we have to learn is how do we handle from the force of interest function to identify the accumulation function. Any question? Right, if you see any of the mistake in the derivation of it, let me know. I was actually running into a block. Not sure where was the, yes.
You might pull up the answer for the just want to see if I.
Oh. Do you know your answer? Okay.
I'm way off.
You wanna try?
My answer was 3.8,
Oh,
so I did something wrong.
the continent's interest and constant annual effective interest rate, Hayward 12, bigger than 0. If the annual effect interest rate is the I equal to 1 over Hayward 25, then
I think it was maybe the substitution on the interval.
See,
Because we ended up with 40 equals VR. And then so it should be the interval of 1 over 2. And then we could be substituting.
if I put in the upper limit, it would be this upper limit of 4 as R, 0 as on. If it's D not the K, if it's a K not in the denominator, it will be a lot easier.
I think it should have been 4 times.
It's 4 over here, but when you see 4 is over here, but we are hoping to get the E to cancel it. So that's why I moved the 4 to the exponents. So for natural log, the 4 in front of natural log is actually the 4 power in the exponent. So if you don't move the 4 over, the 4 will be kind of over here, which will be in the way for canceling. So we won't be able to remove the E notation. That's, if you have an E in your final answer, then you will be able to solve it over here. So like, try to find a way to cancel it. Let's overlook something in the whole process.
Because if you can distribute the 4, and then you just get the natural log R.
Yeah, without the 4, it will be a lot easier to solve. It's possible to expand this. There are definitely a 1 to the 4th power. We would be able to cancel that 1 if you expand the whole thing. But this is going to be a degree 4, and that's degree 1, and they're on different side of the numerator denominator. Eventually, if you multiply the denominator, we end up having degree 5 polynomial to solve. So it's a very, very hard equation to solve. I would feel like numerical solution using a special value of K would be easy. I'll definitely come back to this once I think I had a solution somewhere in my drive, but I don't remember I worked the whole thing out before we tried this question. All right. Let me try to finish the rest This is section 1.2, and then I wanted to try to finish the rest of the chapter 1 and possibly move on to chapter 2. I feel like we've been staying in chapter 1 for long enough, and then the whole book had 9 chapters. All right, but definitely the chapter 1 is foundation of understanding the growth of value, growth of money. So 1.4 is the title is called Quoted Rate for Treasury Bills. Okay, so what do we mean, quoted rate? So it's kind of like an interest rate. When you talk about treasury bill, we're talking about treasury bill in the US and treasury bill in Canada. So a treasury bill is actually a short-term bond that issued by the government. And that's why we were probably using simple interest or simple discount. And this is the introduction in the book. So simple interest and just the simple discounts are normally not applied if you study long-term investment in finance. However, they are being applied for short-term investment. So if you have short-term loans to the United States government or the government of Canada, we may be using simple discount and simple interest respectively. So according to the book, the United States government bond apply using simple discount format, and the government of Canada, they use simple interest format. So even though they are both in a linear format of the function, they're not identical. Right, so the word T-bill or treasury bill, short as T-bill, is a short-term debt obligated issued by a government. By short term, we mean the term of the loan is a year or less. So we have so not longer a year. All right, this is a couple of terminology when you're talking about a bond or talking about a T-bill. There are a couple of terms. So one is the price of the bill. Basically, the price of the bill is how much you pay when you buy the bond, and the money that you paid out is a bond. And then another value is called face value or maturity value. That is the number on the bond that you pay. For example, you might be buying a 1,000 bond or 1,000 T-bill. The price you're paying should be less than 1,000, like 900, 800. So the price should be nominally lower than the face value because you're paying because for you it's an investment, right? You pay less and you get more. And that's the whole point. That's the attractiveness of the investment. If you're paying more than what you get, what's the point of investing it? Another thing is that the increase of value from what you pay to what you get in the end is how to you the value has increased. That increase follow a linear equation. In that linear equation, doesn't matter it's simple discount or simple interest, you definitely have to identify the rate. That is the so-called interest quoted rate. The price of a treasury bill is calculated using a quoted rate. Any question? Right. So how do we calculate it? We're going to look at a formula. This is the US T-bill, and next a couple of examples, we're also going to talk about Canada T-bill. The US T-bill, you can see this calculation, and the F represent the face value, P represent the price in the formula, and then we have days to maturity, means that a year is 365 days. Since we have a short-term investment, we want to look at the long time period of the loan. We want to identify how many days is in there. This is a short-term investment. So this is a calculation for the quoted rate of U.S. Treasury. As you can see, it's following a discount, a simple discount. So this is really a discount rate calculation. If you look at it, remember how do we calculate discount rate? Discount rate is future value minus present value divided by future value, which in this case is a face value. So in the U.S. Treasury, in U.S. T-bill, we follow a simple discount rate. But then since the time frame is shorter than a year, so whatever rate you're calculating, right? so discount rate is similar to interest rate. You have a small amount, which is really the interest. F minus P is your interest. You're going to divide it by the future value. That's your discount rate. And this discount rate is for that time frame. We want to convert it to a yearly annual interest rate. That's why we have to divide it by the number of days, which identified as the interest rate per day, and then you multiply by 360. And it's interesting for the US T-bill, we consider the whole year as 360 days instead of 365 days. So the total interest rate divided by the number of days multiplied by the days in the whole year is a magnifying effect to identify if we expand that time frame to a year, what was the corresponding interest rate? That's the quoted rate. Any question? Okay, so this is follow the simple discount format. And here we're gonna look at a couple of conversion from this. All right, so here, remember the quoted rate can be considered like D. So this is how do we calculate future value if you already know the present value. Remember, future value is larger than the present value, so the present value has to be projected onto the future value. So present value multiply the accumulation function will be your future value. So 1 minus D times T. So this is our time. Number of days divided by 360 is time. And that time, 1 minus D times time is our discount function. If you divide by the discount function, that's kind of like multiplying the accumulation function. So this is accumulating the P onto a future value. Right, over here is discounting the future value onto the present value. So after present the face value or future value, 1 minus D times the T. That's the time that is larger value multiplied by 1 minus dt is discounting future value to the current value or to the present value. So that's the calculation for P. Any question? So if we try to compare that with our simple discount homework, it will be similar to that. All right, so this is a question. Suppose a person purchases a newly issued US T-bill that will mature in 91 days. The face value is 10,000. The question is, if the price is 9,955.676, what is the quoted rate, and what is the annual effective interest rate for the 91 days investment? So first, let's calculate the quoted rate. Quoted rate, first you're going to calculate the interest rate. Your present value is 9,955.76. The future value is 10,000. So subtract these two, obviously we will get your interest amount. Interest amount divided by the future value, there is your discount rate. That's the discount rate for that time frame. So divided by number of days, multiplied by 360, then make it into an annual rate, annual discount rate. So basically, US T-bill is kind of like an annual discount rate. We follow a simple discount model. Any question? So that will be the blue line, blue number are what's identified from the question itself. And then you realize based on what we have, what formula we apply the formula, we will be able to calculate a quoted rate. And then which end up being 1.75% roughly. All right, that's the answer for the first question. What is a quoted rate? So this is the calculation for the quoted rate. The second question is, what is the annual effective interest rate? That is really the I that we want to calculate because it's an annual, it has to be related to the whole year. So here we are. Try to compare that. So if we want to find the annual effective interest rate, we have this equation. This is what we pay right now. This is what we get in 1 year. So our time frame is actually 91/65. So we're using the compound interest formula, present value times the growth factor, which is 1 plus I to the power t equal to the future value. So in this question, the unknown is a I. So we're assuming we're trying to solve the annual effective interest rate I, assuming that we know the I. If that I is given, this is how you use compound interest to calculate from present value to future value. this is assuming we do have an annual effective interest rate and solving the I from that equation, that is the so-called annual effective interest rate. So compare that, we can see that we're using a exponential formula as our formation of the equation compared to that simple interest and simple discount formula that we had in the quoted rate. So in the quoted rate, we're using simple discount model, and the effective annual interest rate, we're using the compound interest model. So using different model, you end up having different solution. We end up having 1.7943, and that is slightly different than the 1.75 from the simple discount. Any question? That kind of echo what our perception before. With the same cash flow, you can calculate simple discount, you can calculate simple interest. And obviously the simple interest is slightly higher than the simple discount. And I kind of echo the comparison that we had last section 1.10. All right, let's talk about Canada T-bill. So for the government of Canada, what's their treasury bill? They're actually using a simple interest instead of simple discount. So there are a couple changes to the formula. In the quoted rate calculation in the US formula, we have F minus P over F. In the US quoted rate formula, we have F minus P over P. So denominator changed because this is a simple interest calculation. When you calculate interest, you take future value minus present value divided by present value. So you divide it by the initial value rather than the future value because you're trying to look at interest. The interest is being compared to the initial value. Another change is the time of the days in the year. In the US model, we're assuming the whole year has 360 days. It's following the bank roll in the US. But obviously in Canada, we're assuming the whole year has 365. So so this is assuming the whole, the quoted rate is slightly higher than the one from US. Any question? So there are subtle change to the formula, identify the P, the F, change it to P, the 360, change it to 65. So we're gonna try to notice the difference. Okay, so for the same cash flow, the present value of 9,955.76, a future value of 10,000. We're gonna try to calculate again about if that is a cash flow in the Canada T-bill, what will be the identified quoted rate? So here is a calculation. Again, the same time, the F and the P, they're all the same, except the formula. Notice that I changed the P there, and then I should change that to 65, but I forget to do it. But what I calculated actually did the time, the number of days is not 360, it's actually 365 in the Canada example. So we're gonna take F minus P divided by P, and then times 65 divided by 91, and then the whole calculation can give us 1.78 as interest rate, which is much closer to the 1.79, right? With compound interest, we have roughly 1.79% interest. Now with the simple interest, we get 1.78%. So simple interest and the compound interest is much, much closer than the simple discount to each other. Any question? So basically, the annual effective interest rate is bigger than the simple interest and is bigger than the continuous compounding interest. Those are the sequence of value in the comparison. This is example 1.14. There's only 2 assignments. I cannot find a lot of example on these. So I only pulled 2 questions for 1.14, and they're pretty much similar to what we did. There's only 2 questions. If you run into any problem, let me know. The calculation would just be identify the rate. Here it is saying using simple interest, even though it's talking about a T-bill. So it's using the simple interest model. So we're not using the simple discount model, even though it was a T-bill. And then in this solution, we also assume the whole year has 360 days. So I think all these examples in this set is actually a combination of both these 2 models. So try it. If you run into any problem, we'll talk about it. Any question? So when you're solving the question, remember you use this, actually this, all right? So we're assuming in a homework, we're assuming the whole year has 60 days. We also are using this for the quoted rate calculation. That's 1.14 is typically a simple interest applied to US bond. And the last section of the whole chapter 1 is inflation. Okay, inflation is also related to finance. We touched on sometime and try to some of our assignment or study are pure scientific and theoretical, and some of the section are deviating away from the theoretical model and look at the reality. Inflation is one of the reality. Okay, so what's inflation? The loss of purchasing power per dollar is called inflation. Basically is what you can buy with $1 and now you cannot buy it anymore. You have to pay more money. That's inflation, loss of purchasing power. So for example, a loaf of bread cost 92 cents in 2005. The price of comparable loaf in the year 2015, so 10 years later, might be about $1. So what you can buy by 82 cents, you have to buy at $1 at 2015. So it would take approximately 10 over 82, which equal to $1.22 in 2015 to buy what you could buy with $1 in a year earlier. So that is the term, the notion of inflation. Any question? So we're trying to put our hands on this phenomenon that's called inflation, but it's hard to do it. So theoretically speaking, how are we going to quantify inflation? People have quoting like inflation rate. This year is how much inflation, of that year is how much. We have historical data about inflation. So how do we exactly get those inflation rates? So here are what we have. Suppose price of things are the focus, right? If the price for one loaf of bread this year is different than the one loaf of bread next year, assuming same quality, then subtraction of those price is how much inflation has gone up. But you want to know you want to know the raw data as your inflation rate. It's called inflation rate. Means got to be a ratio of something. So that differences in price is being divided by the original price. That's called an inflation rate. So here we're going to use R. In the entire section R, letter R is being applied as inflation rate. So that's a mathematical formula for how do we calculate inflation rate. But there's a slight problem. Exactly how do we know PT? So price of at time T is called PT. So there's a question, price of apple, price of bread, price of computer, price of a car. So exactly what is, like which price are we using for determining the inflation rate? Using different price, of course you get a different number for the inflation rate. So here we're gonna say it's unclear how to best define PT. So naturally, we would use something called a consumer price index. It's called an index because it's a combination of multiple items. I assume it has to be a common thing, and we come up with this combined number as consumer price index, in short as CPI. You can search up the word CPI or consumer price index this year and last year and try to see if there's inflation. Okay, so that's roughly the model now. It's not perfect, but we try to make the best of it. Okay, so we're gonna try to look at how we quantify inflation in this relation to interest rate. So here, let's look at how inflation is gonna affect us. If you save some money and earn 10%, this year's 100, next year's 110, you have 10% interest, which means that you have more money to spend. But if there's inflation involved, right, what you can buy with $100, you cannot buy it anymore. So what you planning on to buy with 110, you might not be achieve that kind of purchasing power. So inflation lower your purchasing power. The interest rate increase your purchasing power of the original amount of money. So that's why our interest rate of the investment has to be adjusted based on the inflation rate. So we're going to try to look at how that adjustment happen, or how we represent that adjustment. So I'm trying to explain what is being represented in the book, so I changed the text a little. So here is a pairing. Suppose you can buy at T0 and T equal to 1. So the comparison of the price obviously indicate the change of the value. So here at time T equal to 0, suppose you can buy U unit of something with D dollar. Okay, so the price is D and the unit is U. That means if you only want to buy, if you only want to pay $1 can only buy U over D. That's how many unit you can buy. So that's at T equal to 0. Then come T equal to 1. All right, what will happen is that at T equal to 1, the inflation affected how much money you have to pay for that same amount of products. So 1 plus R is what you have to pay to buy the same stuff. So the same thing you used to pay D dollar, now you pay 1 plus R times D dollar. So that 1 plus R is the factor that affected, they inflated your price. All right, so how much can we pay per dollar? So we're trying to look at purchasing power of $1. It will be number of unit divided by the number of money. So U over 1 plus R times D is how much you can buy. All right, so then suppose, so that these are all about inflation. Now down here, we're going to talk about interest rate. If you have interest rate of I, then if you have D dollar at time 0, it grow into 1 plus I times D at T equal 1. So the interest I allows your money to increase. Now, what you can buy, so how much can you buy with 1 plus I times D dollar at T equal 1? Remember, with $1, you buy this much, right? But then you have this much dollar. So this time, this is how much you can buy. So the purchasing power of that same investment is being predicted. You cancel the D, and then we have 1 plus I times 1 plus I over 1 plus R. That's how many unit we can buy. This is the calculation. So basically, the original increase factor is 1 plus I. Now we have 1 plus I divided by 1 plus R. So the 1 plus I increase value per year is being discounted by the 1 plus R. So they have a division, division relation to the whole growth factor. So we have the so-called inflation adjusted interest rate. So obviously it's making the 1 plus I slightly smaller because we have to do that division, and that's our new interest rate, 1 plus J. Any question? All right, so we often give the J a different name. In this example, we're calling J the inflation adjusted interest rate, and somehow we call the J the purchasing power. So we're like originally what was being apply to I, now we're that's the J. So we often kind of have to look at, when you read a question, we have to be able to identify every number, what do they represent in the formula. We kind of have to learn how to match the formula with the actual question. That's why I'm trying to put specific terminology to them. All right, so let's look at the relation between I and J. I is a intended interest rate, or the interest rate on the book. Say you say your money is growing by 2%, 2.7%. Your bank gave you a documentation, and that's the I on the book. And then J is the one in the underline, the true interest rate earned by your purchasing power. So J is being called the interest rate adjusted because of inflation, right? According to the earlier formula, 1 plus J equal to 1 plus I over 1 plus R. If you want to calculate the J, you have to minus 1 from both sides of the equation. After a little bit mathematical change, if you subtract 1, we have a common factor, 1 plus R, 1 plus I minus 1 plus R, the 1 gets subtracted. We have I minus R in the numerator. So this is our formula for J. So when we have to calculate the J, the inflation adjusted interest rate, this is the second formula. Okay. Any question? right? The other two formula is, these are based on 1 year, okay? But sometimes you have a longer time frame, so it has to from initial time to the terminal time. So the other two formula looks like the same formula as the first two, except all we have to remember is all the quantity, all the rates, the inflation rate, the interest rate. I think I had that one wrong. And they all have to, we switch, we should talk to the book author, right? The numerator denominator was switched. They all have to have a attached time frame. It should be 1 plus I over 1 plus R. What's wrong? Anyway, I copied these off the book. Okay, so let's look at an example how the formula can be applied when you study inflation. And this question says, suppose the inflation rate in 2015 and 2016 were 1.37 and 2.5, right? So these are quoted inflation rate. You can check, like Google, what's the inflation rate today or this year. You might be able to find the inflation rate for 2024. The slated annual interest rate for this person's account is 2.84 during 2015 and 3.27 during 2016. Luckily, both interest rate is higher than inflation rate. You have to realize if your inflation rate is higher than interest rate, you don't get, your money is literally decreasing rather than increase, at least the purchasing power. So let's look at the question A, B, C. A is try to find out what is the inflation adjusted interest rate. So by name, we're trying to find the J based on all the information given. The question A is really solving for the J. B is what is Mrs. Choi's inflation adjusted interest rate for the 2-year period. So this is really counting for both of years, and you have to find out the combined interest rate and the combined inflation rate for 2 years. Those given information in the question are individual yearly interest rate and yearly inflation rate. So B, you might have to work out how to combine them into a 2-year period. C is what was Mrs. Choi's annual inflation adjusted interest rate for the 2-year period. So let's say what C means that the combined 2-year interest rate is not the annual interest rate, but individual year have a different interest rate. And we're combining them to a single averaged out annual interest rate. So let's look at how do we calculate them one by one. I'm going to start with A. Okay, A is asking us to determine the inflation adjusted interest rate for 2015. So it sounded like we are going to focus on 2015. So what I want to do first is to take out all the information in the question and have a more organized way to look at it. So I made a chart. This is all the R value, that's the inflation rate, and this is all the I value for both years. So essentially the question gives us 4 numbers, and we're going to have them all in the same spot. For me, it's easier to grab and apply. So as far for A is wanted to find the J given the I and R. So how do we calculate J given the R? We're using the second formula, J equal to I minus R over 1 plus R. So apply that formula, plug in all the number that we find in 2015. We should be able to finish the calculation, and the final answer is 0.0145. Check the calculation. Let me know if you have any question. So A is pretty much applying the formula for J. This formula is being applied, and we use all the number in 2015. Any question? Any question? Right, I did the 1 plus R simply by combining all together. 1 plus R is 1.0137. Okay, so pretty much the reason I organize this because I feel like it's useful for all 3 questions. So we better just leave it there, and then it's easier to follow once the information is organized. Right. So these are the solution for part B. Part B, the question says, what's Mrs. Choi's inflation adjusted rate for the 2-year period? So this question means we have to have information for both years. We have to find the combined interest rate and the combined the inflation rate. So what I did, you see, this case, we will have to apply the first formula instead of the second formula because we want to combine the interest rate. So interest rate for the first year 1 plus I1 times the interest rate for the second year, 1 plus I2. Those are the I1, I2 in the I row. There's two I number, there's two R number. The denominator is the inflation for the first year, inflation for the second year. If you multiply the 1 plus R1 with 1 plus R2, that's the combined inflation rate or the growth factor for the inflation. So altogether, this division is providing the combined adjusted interest rate. Any question? So these are combined growth factors. So in the growth factor, if you subtract one, you will find the interest rate. But in this case, the interest rate is 0.022122. At least when I shorten the decimal number to 6 decimals, that's what I have. So the part B of the question wanted us to combine the 2-year period and then in a combination we applied multiplication of the growth factor. So that's the answer for part B. Any question? That's the solution. And then we had part C. Part C says, what is this choice annual inflation interest rate? So inflation adjusted interest rate. So we're looking for a I. It says annual means every year in that 2-year period. So assuming that is a I, so 1 plus I to the power 2, it has that combined effect of the growth factor of 1.2212, the one that we calculate in part B. And then from there, if we solve for the I equal to roughly 1.1% each year. That's answer to this. So this I is a hypothetical annual interest rate, which we do not have, that they would just try to forcefully calculate and your inflation adjusted interest rate. Actually, the inflation adjusted interest rate for 2015 and 2016, they're not the same. And the third question, the part C, is forcing us to assume they have the same inflation adjusted interest rate. That's the common number I that we're solving. Any question? Kind of like average out the 2-year to the same inflation adjusted interest rate. So that's the first example in the text. So a little bit of study on the inflation, and then we have the target. So this is how to reach target investment goals. So when you have, if you knew the inflation is going up, and you have an interest rate, so ultimately you have to make sure that your interest rate is high enough to reach your investment goal. So if the bank offer a really low interest rate and then you know inflation is high, you might argue that what's the point of that investment if it's not giving me any benefit? So you might argue for a higher interest rate if it's not reaching your goal. That's why you want to keep in mind what's your target interest rate as your negotiation and also as investment planning. All right, so what do we want to have is that this is the goal. The J prime is what % you want your money to grow. And then here, the I minus R over 1 plus R. This is the calculation earlier that with the J calculation for the inflation adjusted interest rate. So the actual interest rate you are going to have, you were hoping will be bigger than the J prime. That's your target. So, and then we multiply this equation both sides out, and then we realize that I has to be bigger than J prime plus R prime times J prime. So multiply out this equation, we end up having a boundary for the R. So the lower boundary for the I, for the interest rate. Okay, what kind of interest rate will make sure you reach the J prime, which is your goal? The R prime is perceived or anticipated inflation. The G prime is the target investment goal, and then I is projected or proposed interest rate for the investment. We want that to be high enough. We're going to apply that formula for a question. So here we have Tumla wishes to invest 10,000 for 1 year, provided that she can anticipate 4% growth in her buying power. So that's the 4% in growth in her buying power, that is your J. So when you, as we're reading question, you kind of have to label things according to what the mathematical formula that allows your research to work out. She forecasts the inflation rate of the upcoming year to be 3%. So that will be the R prime. This will be the J prime. Okay. Question A, what is the lowest interest rate at which she would willing to make a loan? So if she's giving money to somebody else and she's gonna want money back, that's why they have to negotiate an interest rate. Now, if she doesn't have enough money back, then the investment fail at meeting her investment goal. So the rate is that's the A. The second question, what rate of growth in her buying power does she look forward to if she's able to loan out her money for exactly 1 year at an annual effective interest rate of 8%? So this question is asking for if the interest rate is 8%, if the inflation is 3%, what will be the J? So the B is asking for the growth in the buying power. So it's said, namely, we're calculating J in B. The last question is, what was her actual growth in buying power if the inflation rate for the year was 2.5% and she was able to loan out her money for 8%? So this is when the I equal to 8%, R equal to 3.5%, we're calculating the J. So I think we're reading through the question. It's most important to understand what's being asked and what can be calculated. All right, so we're gonna look at the solution one by one. As for A, we have the anticipated growth in her buying power, which is essentially a J. And then the inflation, which is R, that's 0.03. And then we want to know the lowest rate, which is I. So in this question, and you see these are the two formula in the previous page, you have to identify which formula applies when we're solving this question. Since we have the R prime, the J prime, it looks like the second formula will be useful. So we're gonna identify interest rate, it gotta be higher than the J prime plus R prime times J prime. So we're gonna put in all these numbers, 0.04 plus 0.03 plus 0.04 times 0.03, which gives us a final number of 0.712. So the interest rate that we offer, it has to be higher than the 7.12%. So target. So look at the interest rate, look at the inflation, and you have our plans, and you gotta reach your goal. This is the part A, it's calculation for the I. Now this is a question B. What rate of growth in your buying power? So that's looking for a calculation of J. We have the I equal to 8%. We also have the R, which is the inflation at 3%. So giving all the information that we already have, and we are looking for what we are calculating. Since we're calculating the rate of growth in the buying power, essentially we're calculating the J. So here the calculation, realize to calculate J, you can follow the formula I minus R over 1 plus R. And the rest will just follow the formula by plugging all these numbers. Any question? I tried the homework assignment, they're similar to what we have here. The last question, C. Let's see what was the actual growth in buying power if the inflation is 2.5 and interest is 8%. So that would just be the calculation, J. I think that's pretty much all we have. Time sometimes up. So we're probably gonna end it at the section 15. I was gonna finish the chapter. There's section 16, which is about quotation, like compound annually, compound nominal, or compound continuously. Which one do we do? All we have to keep in mind is that we're gonna convert it to the same price. Like if you all convert it into annual compound annually, then you can compare. If we have different quotation, we cannot compare. That's basically what section 6 is all about. Right, that will be for today. I hope that gave us enough preparation for all the assignment. And please bring out any questions that you might have, because I'm hoping to move on to chapter 2 next week. That way we don't delay in chapter 1 for too long. Right, but if you have any issue with the question, the homework question, please bring that up so we can work on it together. Right, that will be for today. Question on the board, I'll definitely provide solution next time we meet in class. All right, that's it for today. Thank you. Okay.